We're going to be working on limiting reactant problems right now. This is from a worksheet in your packet called Extra Limiting Reactants Practice. And specifically, we're going to be working on numbers 1 and number 3. By the way, on number 2, make sure that you fix this typo that originally said carbon dioxide. I already fixed it on most of your worksheets, but just make sure it says mass of water, not mass of carbon dioxide on number 2. Anyway, we're going to be working on numbers 1 and 3 together right now. I have an abbreviated thing from your notes right here, which is how to identify the limiting reactant. I have my periodic table out, you should too, and I have the mole map. So we're going to jump right into it. In number 1, we're going to treat this like any limiting reactant problem. What we're going to do is we're going to analyze the problem. We have two starting amounts, 34.0 grams of silver nitrate and 22 grams of calcium chloride. All right, the reason this is a limiting reactant problem is we have two starting amounts. Since we have two, we have to figure out which one of those numbers is actually the one that we want to use. One of the numbers is going to give us too high of an answer. The other one is going to give us a lower answer, which is going to be the right answer. The lower answer is always right. Then we get to the mass of the silver chloride. That, at the end, is what we're going to try to find. All right, we already have a balanced chemical equation. We always need a balanced chemical equation in stoichiometry problems. Remember, the big idea in this chapter is that balanced chemical equations are recipes written in moles, and we have our recipe right there. All right, just like I said before, we have two starting amounts, the 34.0 grams of the silver nitrate and the 22.2 grams of the calcium chloride. Which one do we use? Well, first we have to identify the limiting reactant. So we're going to have to convert to moles. We're going to have to divide by the coefficient, and then we know what the lower number to do. We can't just automatically go with the lower number because it's not in moles, and we really need to know what the size of the material is. All right, doing all those steps only tells us what's limiting. We actually have to solve the problem after that. So we're going to, again, one more time, we're going to find out the limiting reactant, then we're going to solve the problem and figure out the mass of the silver chloride. All right, so step number 1 is convert to moles. We're going to write down our 34.0 grams of the silver nitrate, AgNO3. And if in doubt, mole it out. We're going to convert it to moles, and we're going to use molar mass to do it. Why molar mass? Well, you can see down here, if you have a mass and you want to get to moles, you got to use a molar mass. So that's what we're going to do. I'm going to undo here just so we can use that later. All right, the molar mass of AgNO3 has to be looked up on the periodic table. You look up Ag, you look up at N, and you look up O, and the O has to be multiplied by 3 because there's 3 O's. So again, we're going to look that up, and I've added that up, and I got 170 grams. Okay, that's step 1, convert to moles. We also need to do the same thing with the other number, 22.2 grams of CaCl2, that's the calcium chloride. And we're going to add that up. So calcium and chlorine, use 35.5 for chlorine, not 35. And we're going to get 111 grams, and that's a mole. All right. After we do that, we still need to divide by the coefficient. So I'm going to take whatever answer I get for this, and whatever answer I get for this, and that's going to be moles, and that's going to be moles. And by the way, I'm not writing these answers down right now just for the sake of time. And I'm going to divide by the coefficient. Well, the coefficients are up here in the equation. So this one is 2, so I'm going to write 2 there. And this one is 1 because there's no number written, so I'm going to write 1 there. All right, so I just divide to moles, I divide by the coefficient. I'm going to get my answer. This answer is 0.1. And this answer is 0.2. All right, the 0.1 is the lower number, which means AgNO3 is the limiting reactant, and CaCl2 is the excess reactant. Excess is our abbreviation for excess, EXCESS, reactant. All right, so the lower number is limiting, we're set. Now we actually have to solve the problem. We didn't find the mass of the silver chloride yet. So we have to treat this like any old stoichiometry problem now. All right, we've just found out that the CaCl2 is excess, which means that 22.2 grams, ignore it. Matter. It means that there's too much of it. There's more than enough. We're going to have some left over. Instead, we want to focus on the 34 grams of silver nitrate. So we're going to plug that in to a dimensional analysis problem. So we'll do that as our starting amount. And at the end of this whole thing, we want mass of silver nitrate. So at the end of our calculation, we're going to want grams of AgNO3. All right, so how do we go from grams to grams? You look at your mole map, and we have mass, and we have mass, and we're going to have to go through molar mass to moles, and have to go moles to moles and use the mole ratio, and then we have to go up to mass and use the molar mass again. So again, we're going to use a molar mass, we're going to use a mole ratio, and then we're going to use the molar mass again. All right, set up your conversions. All right, the first molar mass, we already figured out that number. It's 170 grams. It's 1 mole. Remember, this is AgNO3 we're talking about here. Okay, the second one's the mole ratio. Well, this is where you might start to get confused. What mole ratio? Well, AgNO3 is part of the mole ratio, and we always go into the balanced equation. And AgCl2, oops, I made a mistake. Silver chloride is the final answer here. All right, so AgCl is what we're going to be going to. So the mole ratio is the ratio of the two substances that it talks about, the silver chloride and the silver nitrate. And remember, we ignored the calcium chloride because it was excess. So we don't care about that in our mole ratio. So we take those two numbers, we bring them down here, and we get that the silver nitrate is what we want in the denominator so it can cancel. See, silver nitrate's right here. So we want 2AgNO3 in the bottom, and we want 2AgCl on the top. I got those 2's right up from the equation. All right, so now AgNO3 cancels, AgNO3. Grams cancels grams. You notice here, now I'm in moles of AgCl. All right, I don't want to be in moles. I want to be in grams of AgCl. So I need to use the molar mass this time again of AgCl. So if I look that up, and I'm going to look on the periodic table at Ag and Cl, I'm going to add them up, and I get 143. You might want to use 143.5, but I'm just using 143 here because there's enough sig figs. Got 1 mole. And finally, the final answer of all this is, let me make myself a little space, 28.6 grams of AgCl. So grams AgCl. So that's the final answer. That answers the question. So we've gone through and done everything, including solving the problem. It looks like a lot of work. Yikes, enough work to make you go cross-eyed, but again, don't get frustrated by all this stuff. It's just we're following the steps. We're trying to find the final answer here. By the way, the possum's name is Heidi. All right, anyway, we're going to go and do number 3 now. Number 3 is a little different from number 1 because we're starting with liters of oxygen gas and moles of pH3. So this one's a little different from the previous ones because it's not grams and grams. All right, we're just going to follow the same steps. We're going to find the limiting reactant, then we're going to solve the problem. We're going to use our periodic table, and we're going to use our mole map. All right. So this time, yet again, we're going to analyze the problem. And when we analyze the problem, we find out that we want grams of tetraphosphorus hexoxide at the end. And again, we're starting with liters of oxygen gas and moles of pH3. So we got to go through the steps here. We got to figure out which one of these is limiting and which is excess. Is 5.8 liters limiting? Is 4.0 moles limiting? I don't know yet. I got to do the steps. So step 1, convert to moles. We're going to do the 5.8 liters of O2. Oxygen gas is O2 because it's diatomic. Brinkelhoff, remember? And 4.0 moles of pH3. We got to do it for both of these. We got to do these steps for both of these. First step, convert to moles. Well, for oxygen, we need to use 22.4 to cancel liters and to go to moles. Remember, we can use 22.4 when we're at STP, no problem. We're just going to assume we're at STP in this problem. All right, and when we do that out, we got to divide by 6. We get moles for our answer. Again, I'm not going to write this number because you can do 5.8 divided by 22.4 yourselves. I'm just saving time. And then we have to divide by our coefficient. So we convert it to moles, check. We need to divide by our coefficient. The coefficient right up here is the coefficient of O2, so it's 6. And when we do that all out, we get 0.43. Okay. Well, now we have to do the same steps with pH3. Well, step 1 is really easy for pH3, convert to moles, because it's already in moles. No need to go any further. Step 2 is divide by coefficient, so we're just going to take that 4 moles and we're going to divide by the coefficient. And the coefficient of pH3 is 4. So 4 divided by 4 is 1. All right, we're comparing these two numbers. We're comparing 0.43 and 1. Well, guess what? 0.43 is a lower number, and the lower number is limiting, which means O2 is the limiting reactant. And that means pH3 is excess. I'm writing out the word excess this time. That means up at the top is 4 moles of pH3. You can ignore it. It doesn't matter. I mean, technically I shouldn't completely cross it out, but we're going to ignore it. So, bye-bye. And 5.8 liters of oxygen is the limiting reactant, so that's what we care about. And we're going to solve the problem now for grams of tetraphosphorus hexoxide from that 5.8 liters of oxygen gas. So let's set it up. This is just a regular old stoichiometry problem now, 5.8 liters of oxygen. I should put the formula here. All right, and at the end of this calculation, we're going to want what it asks us for, which is grams of tetraphosphorus pentoxide. How do I know that this is tetraphosphorus hexoxide? Well, for one thing, it has to be in the equation, so just go look up there. All right, so what's the steps? Well, we're starting with liters this time, and we're going to grams this time. So this time we're going to want to use the 22.4 number. We're going to want to use the mole ratio, and we're going to want to use the molar mass. So again, this time we're going to use the 22.4, which is the molar volume. Then we're going to use a mole ratio, and then we're going to use a molar mass. So let's set up our conversion. So 22.4, the unit of that is liters. So we'll put that in the denominator. And what's special about that number is that's a mole. So we put a mole in the numerator. Now we go for our mole ratio. Well, what the heck mole ratio are we using? Well, we're using the mole ratio of oxygen gas to tetraphosphorus hexoxide. So if you go look in the problem, here's the oxygen gas, and here's the tetraphosphorus pentoxide. And it looks like the mole ratio is 6 and 1. And the 6 O2 goes on the bottom, and the 1 P4O6 goes on the top. Finally, we're going to use the molar mass. Well, molar mass is going to be of the compound that remains. Notice liters canceled liters, O2 canceled O2. We're in moles of P4O6, so that's the molar mass we want, is the molar mass of P4O6. And if I look on the periodic table, here's the P, and here's the O, and multiply P times 4 and O times 6, I get a molar mass of 220 grams, and that's 1 mole, which means that the final answer is going to be 9.5 grams of P4O6. Notice I have my unit over here. All right, so I hope you guys can email me with questions, and we'll go over this in class. Thank you very much.